Hi, my name is Matthew Hossman, and I am the group leader for the Rankine cycle experiment that my group will be performing next week. So first, to highlight the objectives and why we're doing this experiment. The objective overall is to get a better understanding of the theoretical Rankine cycle that we learned about in thermodynamics, and to make observations regarding the different temperatures and pressures and the works and heats involved through different points of the cycle. Why we're doing this is because it is one of the main sources of power gen, both in the United States and in many countries around the world, and is in use still today. To highlight the theory and apparatus that we'll be using to perform this experiment, there are four main stages where these events take place. Step one involves the pump, where work is input into the system to pressurize it and pump it into the boiler. The boiler involves injection of heat into the system, followed by the turbine, where work is pulled out of the system, which is the most, relevant step for the Rankine cycle, and this is where most of the focus is. And finally, the cycle ends in the condenser, where heat is pulled out of the system. Now to show you the PV and TS diagrams for the ideal version of the Rankine cycle. As you can see, the pump is the process in 1 to 2, and turbine is process 3 to 4. I say these together because they have the most in common. 1 to 2 and 3 to 4 are both adiabatic, and that is how we can make observations regarding these two. The boiler process in 2 to 3 and condenser process in 4 to 1 are isobaric, and that's how we can make connections regarding those two as well. This slide highlights the difference between the ideal Rankine cycle and the real Rankine cycle. As you can see, both 2 and 3 and 1 to 4 are still essentially isobaric. However, 3 to 4 is not a adiabatic process here, and so that's a source of some uncertainty compared to the ideal cycle. Now to look at some of the formulas involved in each step. Step 1 in the pump, we're looking at the work input into the system, and this can be observed by looking at the difference in enthalpies between state 1 and 2. The boiler is where heat is put into the system, and we can look at the enthalpies in 3 to 4 here to find that heat. The next step is the turbine, where we can find the work taken out of the system by using enthalpies 3 and 4. And finally, the condenser, where heat is taken out, and we use the enthalpies 4 and 1 for this. To show this slide again, to highlight the apparatus before moving into the procedure, the right side of the screen has a photo of the apparatus that we would have been using had we been doing the experiment ourselves, but I guess that's not the case now at this point. And I guess the procedure on the next couple slides will change a bit as well. So just to highlight some surface things about the procedure on the next couple of slides, as it is quite dense. The first section of the procedure is to be done before any tests and data are recorded, and mostly involves ensuring that each section of the system is in the correct state so that these values are meaningful once you do start the calculation, as well as connecting it to the computer so you can record the data. The next section of procedure involves initializing the system so that you can begin recording the data. Something to highlight here safety-wise is that there is gas being used in the system that if there's a gas leak, you can smell it. So if the lab starts to smell like rotten eggs, we know that something is going wrong in this part here. The last part of the procedure is based on getting the system into a steady state and holding it there so that we can make meaningful observations, and that's what most of these steps are focused on here. Finally, to highlight some of the math behind the system, the top equation is assuming an ideal Rankine cycle and shows that the heat into the system minus the heat out of the system, subtracted then by the work out of the system minus the work into the system, should equal 0. Basically saying that the energy into the system equals the energy out of the system, and these two are in balance. However, for our case and in real life, this is not the case. So we look at something called the thermal efficiency. Thermal efficiency is the work produced by the cycle divided by the heat into the cycle. The heat in occurs in the in the boiler, which, as mentioned before, that formula is H3 minus H2, which is the denominator here. And then the top cycle there, or the numerator, is ends up being the work into the system minus the work out. The process that we use to find this thermal efficiency begins with using those boiler pressures. Using those boiler pressures, we can find H2 and H3. And since we know that the S1 is adiabatic with S2 and S3 is adiabatic with S4, we can use those entropies to find the enthalpies of those states as well. So we have all four enthalpies there, and we can use those to find different works and heats involved in the system, and then end up solving for the thermal efficiency at the end. And then these are my citations.